Okay, welcome everybody. Thanks a lot for staying here with us. Another Tuesday of Quantum Spain. Today is a pleasure to have with us Marco Cerezo. Marco Cerezo is original from Guatemala, and he graduated and got his PhD at the Universidad Nacional de La Plata in Argentina in 2019. Already there, he worked in quantum information research group, mainly in the physics of many-body systems from the perspective of quantum information and quantum computation. Afterwards, he moved to Los Alamos National Laboratory for a postdoc, and in 2021, he became a staff scientist. Since then, his scientific production has bursted, being author of over 80 papers. It is fair to say that he's one of the leading voices of the NISQ-oriented algorithmics, with many papers over 300 citations. I particularly especially enjoyed the variational quantum linear solver paper, I must say. Few persons like him to analyze with a critical perspective the state of the art in the NISQ era. Like Maria Schultz 2 weeks ago, the title of his seminar poses a question. Is quantum machine learning an ill-defined framework? ? It seems that after some years of hustle, the time is right for making a pause and rethinking the foundations. I leave you all with Marco Cerezo. We intend to be done within the next hour, including questions. So questions should be done at the end, but if there is an urgent need for interrupting, please click on the raised hand button and we will unmute you. Also, the chat is there for you to write questions that we will read at the end. Without further ado, Marco, thanks for being here. The floor is fully yours.
Thank you very much for such a nice and kind introduction. And welcome, everyone. Thanks for attending the seminar. Yes, as was said, if you have any questions, just feel free to unmute yourself and ask them. The seminar is supposed to be a little bit provocative. So, the more chance we get to engage in a discussion, the better that's going to be. So as the title says, I'm going to be talking about whether quantum machine learning is an ill-defined framework. And the outline of the talk is I'm going to be giving a very brief introduction to quantum machine learning. I understand that there's already been a few Quantum Spain seminars about quantum machine learning, so I will try to not linger here too much. Then we're going to discuss some of the issues of quantum machine learning and why I personally am becoming a little bit cynical about the perspectives of parameterized-based quantum circuit machine learning, quantum machine learning. Then we're going to talk about new opportunities for quantum machine learning and some outlook and closing thoughts. So first, a disclaimer that I want to give. This talk is going to be very opinionated. This is by design. I will try to just shed the light in some of the probably many issues of quantum machine learning. And I don't want to do this in the spirit of being mean or the villain of the story. It's in the spirit of us engaging in a thoughtful discussion about whether what we're doing, whether we can expect something useful from what we're doing. And of course, the idea is to try to inspire people to prove me wrong or to come up with new ways to do quantum machine learning. And, at the end of this talk, I'm going to be presenting some results that we've recently had about maybe different ways of thinking about quantum machine learning. So first, let's begin. And of course, if you're attending a talk of mine, you know that I'm going to begin with a meme about quantum machine learning. So extremely briefly, in one slide, the high-level pitch of quantum machine learning. We already know that machine learning is this technology that has been extremely successful. We now I think it feels almost like we're getting pushed AI pretty much everywhere where companies can. And this technology has not just revolutionized the way that people write grant proposals nowadays, but also the way that we do science. Machine learning, I think, is used in pretty much all the areas of research in both like industry and academia. And we also know that we have this technology, which is called quantum computing, which can, in a way, overcome some of the limitations of classical systems for certain extremely specific tasks. And I want you to keep this in mind. And the question is whether we can use the formalism of quantum mechanics and quantum computing, combine them with the learning methodology of machine learning to somehow try to overcome the limitations of standard classical machine learning. Now, this is a very big claim because the hope is that maybe quantum machine learning can outperform their classical counterparts on learning tasks. This, of course, we know that there are some examples where quantum machine learning could potentially give some advantage. But the question is, can we use quantum machine learning for some, if not all, the problems that classical machine learning has been proposed to, which I feel is kind of like the trend that our field is going into. So again, this seems very broad. And when I shared the announcement for this talk on Twitter, which I refused to call X, someone mentioned, well, but what do you define? What is quantum machine learning? How do you define it more specifically? And which type of quantum machine learning are you thinking that it might be ill-defined? So the problem is that quantum machine learning is very much a blanket term. Pretty much anything where you just take a quantum computer and you use a little bit of learning methodology, we can call this quantum machine learning. And maybe you've already seen this plot, and maybe you're already sick of seeing this, but the main idea is that quantum machine learning can encompass this wide range of problems where maybe the data type that you have is classical, or it might be quantum, and the algorithm that you use to solve a problem might be also classical and quantum. So in this quadrant of classical, we might have like tensor networks. They're a purely classical method that are inspired by quantum mechanics. So this could be sort of like something that is in classical. What is an algorithm that is classical? It's whose data is aiming to be quantum. Well, let's think about compiling a quantum circuit. You have a unitary that you want to implement in a quantum device. Here you're going to do a compilation classically, and those gates are going to implement on a quantum computer to do something that you couldn't do otherwise. But for the purpose of this first part of the talk, I'm going to be focusing on the second part, which is we're going to be using quantum algorithms to try to learn from data. And in particular, I'm going to be focusing on whenever we have the problem of I have a classical data set, those may be pictures of cats and dogs, those might be financial data, those might be events from some particle accelerator, and we want a quantum model to try to learn and extract information from the data. And of course, we also have the problem where our data is quantum in itself. Maybe we have a simulation that we're running, and we can do some traurization of an evolution, and we can prepare some states of interest, which already live inside of a quantum computer, and we're going to try to process and learn from them therein. And here, the first part is going to be discussing some of the issues of the algorithms here. And at the end, hopefully, I'm going to try to convince you that maybe where we should be looking is kind of like this top right corner, where we have really great classical algorithms, and maybe we should just like pad them with quantum information and measurements or data that is coming from a quantum computer. So the classical paradigmatic like scheme that and the diagram that you will see for geometric quantum machine learning, again, is this idea that you're going to take a problem of interest and I'm going to encode it into a learning task, because we don't know how to solve it explicitly. I can't just write a quantum circuit that is going to take an input and is going to give me the output that I want, because maybe it's not obvious what each gate is going to be doing. So we just encode this into an optimization task, and we're going to try to train a parameterized quantum circuit, sometimes called quantum neural network, to solve this task. And why would we ever want to do this? The most common claim is that the quantum Hilbert space is kind of like this very exponentially large space that can serve as a feature space where you can just explore and analyze data in this sort of hybrid framework that we see here. So here, the idea, as I said, you have some problem, you might have some training data, you're going to define a cost function that quantifies the extent to which you have solved the problem, and you're going to use a quantum computer, essentially in the form of a parameterized quantum circuit. You're going to take some quantum states, which might already be prepared on a quantum computer. They might encode some classical data, and I'm going to send them through a quantum circuit that, in a way, is going to try to emulate the action of a neural network by having a certain set of parameters that are trainable. Then, by making some measurements at the end of the circuit, this is, again, something that might seem obvious, but you might be surprised how much this part is ignored. We're going to try to extract information from the quantum computer. We're going to create an estimate of our loss function, and we're going to use classical optimizers to get the new set of parameters, turn the knobs in the circuit to hopefully get us closer to the solution. After many iterations, hopefully we're going to be able to solve the problem and get the output that is appropriate for the problem that we're trying to solve. Now, this quantum machine learning variational algorithm paradigm has been proposed essentially for all the tasks that you can imagine. If you have a task, it's actually not really hard to just create a quantum algorithm, define a cost function, which is going to encode your problem, and then you can just try to solve this. And for the remainder of this task, of this talk, I'm going to assume that what we're interested in and the thing that we're computing in the quantum computer are going to be basically quantities of this form, which is going to be some quantum state, that is evolved with a parameterized quantum circuit, and you measure the expectation value of some observable O at the end of the circuit. Of course, if you have data, you might have multiple input states, multiple measurements. This might also depend on, say, classical data if you want to do data re-uploading. But let's just try to get to the simplest case, because I think that the lessons learned here are going to be applicable to wider ranges of scenarios. And of course, we can always take a bunch of these quantities, do some classical post-processing to them, and just construct our loss function from this. But at the end of the day, this is what we're going to be estimating on our quantum computer. Now, over the past years, there's been a lot of hype for variational quantum computing. The idea of VQE, which kind of jump-started all of this in 2018, was this idea of training a parameterized quantum circuit to solve the ground state of a given Hamiltonian. And this is huge. This is one of the biggest tasks that we have, because it can be used for quantum chemistry, material sciences. So if we're actually able to prepare ground states of some Hamiltonian of interest, and we can do this in this variational perspective, then this is great. You can see that the number of papers that use variational quantum eigensolver VQE, it's kind of like this very nice exponential curve going up. Maybe it's quadratic. I'm actually not sure. I'm not going to claim exponential because we probably don't have enough data just yet. And then we can also solve optimization problems with the quantum approximation optimization algorithm, also called QAOA. And you can see that this is also attracting considerable attention, quite a bit of papers in this field too. And if we think about quantum machine learning, this is just blowing out of the water. The number of papers out there that are just using quantum machine learning in one way or another is just, just 2024, we're about to reach 600 papers in this topic. And the whole point is that a lot of these works are claiming that we can use these methods to achieve some form of quantum advantage. And this would be great. And the question is, well, we have all of these papers. There's so many claims of quantum advantage, but what do we actually have to show for all of this? What are the problems where we can honestly say we believe that there's going to be a quantum advantage here? We have a demonstration that once we have a sufficiently large quantum computer, say like 100, 500, 1,000, 2,000 qubits, we're going to be able to really solve a problem. And that's going to be it. And the thing is that I'm not certain that we have that. And yet you see all of these curves going up. So, it kind of makes you wonder, why do we have these very nice trends going up? There's a colleague of mine, Zoe Holmes, who said a quote that I really, really like, which is that in a way, variational methods have democratized quantum computing. It's honestly not too hard to see that, because this is a paradigm that can be used to solve any problem that you have in mind. It's very easy to use. And not only that, for students, it has a very easy and gentle learning curve. If you know a little bit of Python and linear algebra, you have pretty much everything that you need to start working on quantum machine learning. And, this might be a good thing, this might be a bad thing, and this is the way that classical machine learning works. So why not quantum computing? Why not we just do the same thing? But again, for me, the question is, we've been training parameterized quantum circuits for so long. What have we to show from this paradigm? And to be honest, it is very hard to tell what it is that these methods can and cannot do. And I could just spend the whole remaining of this talk talking about the issues of parameterized quantum circuit-based quantum machine learning. And I've talked about this quite a bit over the past 4 or 5 years. And, these are some of the issues, which I'm definitely not going to get into detail here, because I think that if at this point you don't know about some of these issues, then I think that it might be because of a more positive bias than just like lack of literature search. For instance, we have that answer to say, how do we build parameterized quantum circuits? This is a very much non-trivial question to ask, and at the heart of so many issues. If you have classical data, how are you putting it inside of a quantum computer? Whenever we have classical data and we do a simulation of an 8 to 10 qubit quantum computer, classical data is huge, and we have information bottlenecks. Quantum computers will never be useful for large data sets with massive amounts of data, because those needs to be encoded in the quantum computer. And in the near term, while we're doing our simulations on small problem sizes, our data is too massive. So I usually see people do like PCA and then put the results of PCA inside of the quantum computer. Well, the problem's already kind of solved. PCA did all the heavy lifting. So what is the quantum doing at that point? if you're training this cost function, we know that local minima are going to be everywhere. This is one of the biggest issues. I think Maria talked about this a little bit. How do we compare quantum machine learning with classical machine learning? I think that honestly, most of the approaches that we take, where we use like classical fully connected neural network with the same number of parameters, that is for me a very ill-defined problem. We don't have scale analysis. Quantum computing is all about scaling, right? Because we need to know if when we go to larger problem sizes, this is going to be exponentially expensive or not. And if you solve a problem for just 12 qubits, then we just have no idea how hard it's going to be or how this is going to scale whenever you go to 50, 100, 1,000 qubits. This is one of the pet peeves of mine, which is we need to do measurements in a quantum computer to extract information. And if we do a simulation of a quantum machine learning model and we don't use samples, then we're already in very deep trouble, because this is never going to be representative of what a quantum computer can do. It's okay if you don't want to add hardware noise, but no-shot noise is at the very basic level a huge issue. And if you've ever trained a quantum machine learning model with and without shot noise, you're going to see that it is a very different beast that you have to tame then. And of course, I already mentioned it, hardware noise. Are we aiming to apply quantum machine learning models in the near term? When there's going to be maybe just error detection, or still going to be we're going to have a little bit of noise. What's going to happen there? How is our model going to perform? And even if you assume that you're going to run your quantum machine learning model in a fault-tolerant quantum computer, I think that there is a disconnection between those two things. Because I don't know if you've thought about this, but variational quantum algorithms and quantum machine learning models, you do parameter updates, and a lot of times those parameter updates are kind of very small changes in your parameters, especially whenever you're fine-tuning near the solution. But have you ever thought about how to implement a very small angle rotation on a fault-tolerant quantum computer, which can implement Clifford gates and requires T gates that you somehow need to get? It's going to be extremely expensive. So I don't even know if the way that we're doing quantum machine learning currently is a paradigm that can just be easily translated to fault-tolerant quantum computers. So even if we get fault-tolerant quantum computer, it's not like, okay, all the noise is gone from my algorithm. It's like a simulation, so everything's good. We're incurring in massive overheads because of how we're planning to do quantum machine learning. And of course, Barren plateaus, this has been the thing that has been haunting my dreams for the past 5 years, is this problem of you have exponentially concentrated loss functions, and more recently, the problem of classical simulability. So if our quantum machine learning model is working, how do we know that it's not classically simulable? And I'm going to talk about these two very briefly, just because the way in which we got to our new paradigm for quantum machine learning is by realizing what are the issues of the previous paradigms of quantum machine learning. So I want to sort of like take you through this kind of like path that math took us in. So hopefully you can understand why, once we get to the end of this talk, why it is that we're doing what we're doing. So very, very briefly, let's talk about Barren plateaus and classical simulability. And it's been 5 years since we've studied Barren plateaus. At first, we kind of understood this phenomenon as sort of like independent. There were different sources that created Barren plateaus. Maybe it was noise, it was certain types of measurements, certain types of circuits. But I think that after a while, we have a pretty good understanding of this phenomenon. We have this review of Barren plateaus if you're interested about this phenomenon and you want to learn more. But morally, what I think, and I feel pretty confident in saying, is that Barren plateaus are just a curse of dimensionality. Because, after a while, once you have a bunch of models that you can prove that are going to have Barren plateaus, they're not going to be scalable, because you're not going to be able to train them when you get to very large problem sizes. You can ask the question, what do they all have in common? What do all of these models that have Barren plateaus have in common? And what we realize that it's a curse of dimensionality. And again, if we remember this sort of thing, that this quantity that we want to get from the quantum computer, which is the expectation value of an observable, this is just the Hilbert-Schmidt inner product between two vectors. Think about rho of theta and O, say in their Pauli basis decomposition. So these are vectors of size 4 to the n in this vector space B, which is just the space of all bounded operators. So if you take the inner product between these two exponentially large vectors, you get our loss function. So this is a problem because the inner product is in a way a similarity measure. It's just telling you I have two vectors. How close are those two vectors? How similar either? And this, from day one, since we saw the first papers in variational algorithms and we saw these type of loss functions, we should have been worried. Because on the very, very general assumption, if you take two exponentially large vectors and you compute their inner product, this is bound to be exponentially small and concentrated. Because if I take two vectors and I change this a little bit, the inner product is not going to realize because it's just too big of the space that we're living in. So, just by that, we can just kind of like intuitively understand Barren plateaus are a curse of dimensionality. So in a way, the same feature that we wanted to exploit, which was this exponentially large Hilbert space where we want to process information, is the very same thing that is causing us issues. And how do we avoid Barren plateaus? So again, we had a bunch of methods to avoid Barren plateaus. We proposed quite a few of them, but after a while, we again had enough of them to just take a step back, stop looking at the trees and start looking at the forest. And we asked the question, what do all of these methods that avoid Barren plateaus have in common? And the realization, what we did was, okay, Barren plateaus, we know that they are a curse of dimensionality. So whenever you don't have Barren plateaus, it's because your model essentially operates in a very small polynomially sized subspace of, say, this operator space or the Hilbert space. But there's always this intuition that you avoid Barren plateaus by, instead of looking at this very large space, you just look at a much smaller space. And now your vectors are vectors in this polynomially small space, and they're just kind of like random vectors in there whose overlap is expected to be 1 over the dimension of the space, so 1 over poly. So whenever we say, oh, this model doesn't have Barren plateau because the variance decays as 1 over poly, it's still the worst case. It's just the worst case in a polynomially small subspace. But then once you have a polynomially small subspace, you kind of realize that this has to be classically simulable one way or another. So essentially and morally, what we did was we took all of these models that don't have Barren plateaus, and we can sort of intuitively see that the information processing capabilities of the parameterized quantum circuits can be implemented on a classical computer, and they can be emulated by an algorithm that runs in polynomial time. So more specifically, we thought about these two frameworks. So the previous one, the one where we showed in quantum machine learning on this scheme that you're probably already bored of looking at, is you have the problem description, you put it inside of the quantum computer, you make some measurements, you feed those into the classical computer, and you get an estimate of your loss function. And by repeating this loop, you're going to train the parameters in your loss function. And note that even here in standard quantum machine learning, I call this an estimate because we're doing finite samples. We never can get to absolute precision the expectation value of an observable over a quantum state. So even in our standard setting, we're always estimating the loss function. But now let's think about this paradigm. It's slightly different, and this is the one that we're going to be focusing on from here onward, where I give you the problem description and I give you an initial data acquisition phase. During this initial data acquisition phase, you're going to be able to use your quantum computer. You might be able to make some measurements. This phase takes no more than polynomial time. You make a polynomial number of measurements. You store them in a polynomially sized memory. And once this phase is over, you lose access partially or completely to the quantum computer. And here the rest needs to be done on a classical computer. And in our case, if this is a variational algorithm, once the initial data acquisition phase is over, we put this in a classical computer. And then for different sets of parameters, we can estimate the loss function classically. And what we showed was that a lot of those Barren plateau-free models, they can be put here. But the thing is that it's not like quantum computers are not needed. What we saw was that we still kind of need this initial data acquisition phase one way or another. In some cases, more than others. In some cases, we don't even need the initial data acquisition phase, and the whole thing is classically simulable. But in most cases, the quantum computer is still needed. And of course, this doesn't mean that if you have a loss function that is not concentrated, there's not going to be a Barren plateau, because there's always an argument to be made that you can cook Schur's algorithm into a quantum machine learning model that is not going to have a concentrated loss function, and this cannot be classically simulable. Yeah, we know, we actually built this in our paper, but these are not what we do in practice. These are just like mathematical constructions who have some proofs, but are they useful? I don't know. I don't think so. Maybe we can borrow inspiration. But for me, what was cool about this paradigm is that it connected really nicely with this Google paper called The Power of Data in Quantum Machine Learning, where what they showed is that if you take the set of problems that a classical algorithm can solve in polynomial time, BPP, the set of problems that a quantum computer can solve in polynomial time, BQP. But now you ask the question, if I take a classical algorithm and I feed it with information, measurements, samples that are coming from a quantum computer, well, this is strictly more powerful. And this I was very excited to see, because that means that maybe there's still a way to get like meaningful quantum advantages in this top paradigm. Again, because quantum is very important. This is pretty much all that I want to say on this topic. If you want to learn more, I encourage you to see Zoe Holmes' talk on Quantum Spain on this connection between probable absence of Barren plateaus and classical simulability. That paper was very high level. We thought that this connection was going to be there. Then, of course, referee 2 told us, well, you're just saying that this is classically simulable. How do you know that it is actually classically simulable? So we're taking different models. We're doing their classical simulation, and we're doing proof by construction. And I also encourage you to go see Pablo Bermejo's talk. I think all of these are saved in the very nice YouTube channel for Quantum Spain, which I encourage you to check. It's full of amazing talks. And in this paper, we took quantum convolutional neural networks, and we showed that those could be classically simulable end-to-end. We just need a quantum computer to get some information via shadows, and then we don't need to run a quantum convolutional neural network in a quantum computer. So in my mind, QCNNs, quantum convolutional neural networks, they're fully classical. Like there's been recent papers that are trying to claim otherwise, but I'm still to be convinced. And in my mind, we should never use quantum convolutional neural networks because they can be completely classically emulated. So just to wrap up this first part, what are the issues with quantum machine learning? And again, take this with a grain of salt. This is my personal opinion. A lot of this is just personal biases, which is that I see Barren plateaus as a symptom of a deeper issue. This is a problem that we have very, very large exponential space. And if we're not handling it properly, we're just getting issues like Barren plateaus. And the way that we solve those issues is, well, let's not use the whole exponential space. Let's just use a small space, and then we get classical simulability. And this reminds me of this quote from Scott Aronson, which I know he constantly says during his talks, and it's also in his blog. You can see the entry down there, which I'm certain is going to be most of them, is that in a quantum algorithm, it's kind of like this very carefully choreographed patterns of interference where you're trying to take the probability of the correct answers to be amplified and the probability of the wrong answers to have destructive interference and just go down. And this is what quantum algorithms do. And doing this requires very purposefully constructing circuits where each gate has a specific role that it's playing in this sort of overarching orchestra of quantum gates. But the question is, what we're doing that when we run parameterized quantum circuits, this is absolutely not what we're doing. It's just kind of like bashing this exponential large space, and hopefully something is going to come out of this. And I think that in a way, parameterized quantum circuits get the worst of both worlds. In quantum, because you're just like throwing stuff in this exponential large space and hoping that something will come out of it. And it also doesn't have provable guarantees, just like classical machine learning. So I think it's kind of like in a very awkward space. And for me, I feel like, I wonder if this is not telling us something very deep, because at the end of the day, math is math. Math doesn't lie. Math doesn't have a personal opinion. So when we see all of these issues popping up, I wonder, are we using the wrong tool? Is this idea of trying to coherently process classical information or just any type of information in a quantum computer? This feels kind of wrong. And as a fun anecdote, I was chatting the other day with my brother. He's a biologist, and now he's studying economy. And I was mentioning all of these issues. And he was like, well, you're trying to emulate classical algorithms and the way that classical algorithms work on a quantum computer. So your inductive biases are those of classical algorithms. And he mentioned, so isn't it reasonable that the algorithms that work are those precisely that are classical? And I just kind of blew my mind. I don't know if this is true or not, but I just want to leave you with this thought that if we're emulating classical in quantum, doesn't it not make sense that the thing that is going to work is precisely the ones that is classical? I don't know. This is maybe just me like speaking up there. So the question is, where does this leave us? Well, of course, there's a bunch of caveats to our arguments, and we can spend days poking a hole at them. Like warm starts, are those going to be able to solve the problems of quantum circuits? I don't know. I'm overly pessimistic about them. We're working on a paper where we show that people say, oh, I found this way of initializing my circuit that has large gradients. So now I can train, and the solution must be nearby. we found exponentially many families of continuous families of ways to initialize the circuits which have large gradients. So do we need to explore them all now? I feel like it's just like the exponential scaling is just being pushed somewhere else. And Scott Aronson also says that there's this law of conservation of weirdness or complexity. And I think that if you have a hard problem, you might just likely be pushing your complexity from one place to another. So will quantum machine learning never work? I don't know. I definitely do not know. And I'm not claiming that quantum machine learning will never work. Maybe there are some super fringe cases, and maybe we'll never have guarantees. But if we find somewhere where we train a parameterized quantum circuit and it works, I'm going to be very happy about this. I certainly will be very happy about this. But in the meantime, I wonder if we shouldn't just go back to the drawing board and just, again, let's look at where math is pointing us. Literally trying to solve Barren plateaus pushed us to classical algorithms with quantum data. It pushed us to classical shadows and giving those shadows to classical algorithms. So why don't we pull on this thread just a little bit and try to see where we get? And this is where I'm going to be discussing some results that I'm going to say cautiously optimistic about. You're not going to hear me make any big claims here. This is not what I'm here for. I'm here for hard rock solid science, and the results that I'm going to show you are mostly preliminary. So I'm going to give you the following learning problem, and we're going to see how we can fit it in this paradigm that I previously presented. So again, we have this framework. So consider this learning task. I'm going to give you a set of quantum channels. Let's call this curly C, and a probability distribution P over this set of curly channels. And what I'm going to do is I'm going to sample a single channel from this set according to the probability distribution. And that's going to be the not curly C. Then I'm going to give you data sets of quantum states that are parameterized by some real value parameter. We can make this more complicated. This can be multi-valued parameter, but let's do this in the simplest case. And let me give you an observable O. This is the setting in which we're working. So now during an initial data acquisition phase, which again, I'm going to assume doesn't take more than polynomial time, I give you access to a quantum computer, a training set that belongs to this full set of quantum states, and access to this channel. And here you can do whatever you want. Once the initial data acquisition phase is over, you don't have access to this channel anymore. So in this case, we're going to lose only partial access to the quantum computer because we can no longer implement the channel. But you can still access the rest of the states in the data set. And what you need to do is you need to take the data that you got from the preliminary data acquisition phase, and you need to be able to predict the expectation value of any state that has been sent through the channel and measured over O. And you need to be able to do this for all the states in the data set. So I'm going to just take a sip of water and let you ponder about this for a second. Okay, so how would we go about trying to solve this? And the goal is to try to use as few quantum resources as possible. Well, some ideas is you might just do brute force process tomography. You forget about the data set, you forget about everything, and you're like, okay, there is a channel that I need to learn. I'm going to try to learn this channel. Yeah, you could absolutely do this, but this could be prohibitively expensive. And it also, it doesn't use any of the additional information that I've given you, which is information about the set of channels, the probability distribution, the data set, or the measurement that you're going to be interested in. So maybe you're also interested in incorporating knowledge, and maybe if I tell you, okay, this is an ensemble of unitaries, and I give you some properties of this ensemble of unitaries, you could try to do Hamiltonian learning, and this is better. You're starting to incorporate knowledge. And the problem here is that, again, you're not using information about the probability distribution S or O. So what we're trying to tackle is, how can we use a framework where we use all the information that is available to us, all C, P, S, and O? So the solution that we came up with was Bayesian inference. And this might sound like, this big build-up to Bayesian inference. It almost feels like, like not interesting. But let me try to convince you that this is actually super cool. So in particular, what I want you to do is think about this expectation value as a random variable. So what do we mean as a random variable? Well, it does depend on some channel that was sampled from some ensemble according to a probability distribution. So now think about this as, it could have been a different channel that I sampled. So overall, this is a random variable. And the question that we're going to ask is, what distribution does this random variable have? And more generally, if I give you a set of expectation values for different states, those could be those in the training set T, what distribution does this vector of expectation value have? And what's pretty cool is that in this paper right here, we see it's actually quite old, and I'm going to explain why it is that I'm now just starting to talk about all of this. In this paper, we show that under certain conditions, this probability is going to be a Gaussian distribution, where the mean is just the expectation value, and sigma is just the variance over your distribution. So this is really nice, because this gives us a lot of information. And something that I want you to notice is that this expectation value, of course, depends on what is the channel that you sampled. But once you take the expectation value, mu and sigma squared, they must be independent of C, because we've kind of like averaged it out. So think about U and sigma squared as just completely being independent of C. They don't contain any information about what is the actual channel that we sample. They just tell you, okay, this is a normal distribution that is going to have some mean that depends on what is the probability distribution and what is this ensemble of channels. And more generally, if now you have a vector of observation, this is going to be a multivariate Gaussian distribution, where you have the mean vector, which is just the mean of each one of those expectation values, and sigma is the covariance matrix. So now we think about, well, by definition, now V forms what people call a Gaussian process, just a multivariate Gaussian. But this, at the same time, it unlocks the predictive power of Gaussian process regression into what we're calling quantum Gaussian process regression, which is like, we're not, and this is something very important to mention, because in classical machine learning, people use Gaussian process regression for, say, predicting the prices of houses. And they don't have a proof that the underlying distribution is Gaussian. They just assume that if you have very large data sets, the central limit theorem is going to kick in and everything is going to kind of converge to Gaussians. We have a proof that this is Gaussian, that the underlying distribution is this. So using Gaussian process regression is using the correct tool for the correct problem. So how do we solve now the learning task with our paradigm? During the initial data acquisition phase, all that we're going to do for now is just compute the expectation values. Take the states in the data set, send them through the channel, measure the expectation value of O up to a given epsilon precision. And that's it. That's all that we're going to do. And, it's kind of like the simplest and dumbest thing that you can probably ever think about doing. It's just like, oh, I'm just going to send states through the channel and measure the observable of interest. And this is, of course, just for the data set. And I'm going to compile those results. Now, you can do this during the initial data acquisition phase or later on, but eventually we're going to have to compute the entries of the covariance matrix for all pairs of states in the data sets. And I'm going to explicitly go there in a second, but remember, these guys are independent of C, so I could just do this once the initial data acquisition phase is over. And computing these inner product, this is just essentially some simple inner product. And I'm going to go to an example in just a second. So once the initial data acquisition phase is over, I give you a new state that belongs to the test set S, and it's likely not in the training set. So we already know, because we've already proven that if I just take this state on its own, its distribution is going to be that of a Gaussian. We've already said this in the previous slide. But of course, this contains absolutely no information about the channel. We've already said that this mean, this sigma squared, they don't have any information about C. So this is completely useless for prediction. However, the power of Gaussian process regression is that we can update our prior information with our observations. So we can ask the question, what is the probability of this new observation, given that I have measured the expectation value for a bunch of states in my training set? It turns out that if you do the math, and it's not terribly hard, the probability, the conditional probability, or your posterior distribution is also a Gaussian. And this is just because if you take a multivariate Gaussian, you convolve it with a Gaussian, you get another Gaussian. These have very nice properties. So this posterior distribution is also Gaussian, and you update the prior in this way. and you update you get a posterior mean and a posterior variance, whose expressions are here. And now what's really nice about this is that we can see that the posterior mean does contain information about C via our vector of observation. So now we are definitely including information. Also, very interestingly, we see that this is a positive quantity, this is a positive quantity, this is a negative number. So we have reduced our variance by using information. And this completely makes sense, because what we're doing is we're incorporating previous knowledge about observations and thus decreasing our uncertainty. So we're using all the information that we potentially have, because we are using the information about what is the set of channel C and the probability distribution to compute these expectation values. We are using our observations and the information about O and C in this vector, and we're using information about the data set through this covariance matrix and the entries of this vector K, which is just the covariance matrix, which is telling me how similar is my new n+1 state to all the states that were in my data sets. And again, this is independent of C. I don't need a quantum computer with access to C to compute these guys. So again, this is a true quantum Gaussian process. We've proven from first principles. It's not like we are using Gaussian process regression to solve this task. This is the right tool to use to solve this problem. So in wrapping up, I'm going to show some preliminary results. So say that now I give you C is just a unitary group of the Greek Q. Note that this is not the full dimension of all Hilbert space. So if you have n qubits, Q does not have to be 2 to the n. You can just have a unitary acting on a subset of qubits, and P is associated Hart measure. Well, the entries of the covariance matrix just look like this. Again, you can see it's independent on what is the unitary that I sampled according to the Hart measure, and it's just a simple inner product. And this can be evaluated with a simple swap test in a quantum computer if I have access to the data set. Now, of course, this is only going to be efficient if Q is at most log n, because if these are exponentially small numbers, I'm not going to be able to do any training. And this is kind of very dumb, but this is what we didn't realize in the first version of our paper, this paper right here that I'm showing at the bottom, where we said, oh, if the unitary group is acting on all the qubits, then this is inefficient. You're not going to be able, you need to do exponentially many measurements to compute the entries of the covariance matrix, so you cannot use this Gaussian process. But then we realized, wait, but we don't have to predict global observables. We can only predict local observables. And if I'm interested in predicting local observables, then this becomes efficient. And we've actually submitted an updated version of this paper to arXiv. It's going to go live, I think, tonight. And for instance, in this case, what we're doing is this is our data set. This is the prediction that we're trying to do. This is 25 qubits on a square lattice. And we're trying to do some interpolation where these are of observations. And this, you can see that there's a couple of lines maybe explaining it here. The dashed line is the true expectation value for the data set. The solid line is our prediction. And this interval that you see here is our 2 sigma 95% confidence interval. So you can see that we can do interpolation and we can do extrapolation with this. And if this doesn't sound or seem too cool, just give me a second. Then we can also do this with 200 qubits, which is already starting to look a little bit nicer. So here we're predicting an observable, I think, on 8 qubits out of 200. And you can see that by observing points here, we kind of predict this twist and bend right here. And we can do this very nicely. But let's try to push this a little bit further. Let's now consider that I give you a free fermionic evolution. And you're just going to sample some free fermionic evolution. Now we find that we can predict efficiently low-order monomials of Majoranas. And this is something that a summer school student for last year's summer school, this year's summer school has been working on. So this is a paper that we're currently finishing. And you can see here that if we don't have any training points, this is our prior observation. It's just a line that is independent of the data. And you can see that the confidence intervals are really bad. Now, as I hit play, you're going to start to see that we're going to be including different number of training points. This is a simulation on 8 qubits. And you can see we put 1 training point here. Now it gets a little bit better, 2, 3, 4. Starts to get a little bit better. And by the time we get to 8 training points, let me see if I can. OK, there it is. You can see that with order and training points, we can do this prediction where now we're really hitting all of this kind of like intricacies of our data set. Remember, those states rho of t, they can be completely arbitrary. And here we just made like very random parameterized initial states just so that we can get a very complicated function. And this is what we get. So I know I'm getting to 8:45, so I'm going to try to wrap up soon. And the question, well, yes. I heard someone. If not, I can try to wrap up and we can go back to other questions. So the question is everything a Gaussian process? Because if everything is a Gaussian process, then nothing is a Gaussian process, and it's not interesting. So will we always get Gaussian processes? Well, no. It turns out that there's a lot of cases that don't lead to Gaussian processes. The easiest one is just pick your observable to be a projector, like a bit stream, and you can get like Porter-Thomas distributions, which are going to be exponential. But also, if you take certain sets of observables, like 4 Majoranas and a free fermionic evolution, this is not a Gaussian process. And so it's not obvious that this is a Gaussian process as an effect of large numbers or just like central limit theorem. In fact, we show that it is not a central limit theorem problem. And there's a lot of things that are not going to be Gaussian process regression. And again, it just feels like we're using the right tool for the right job. And for me, this is kind of like the holy grail of Bayesian estimation, because you have a guarantee that the underlying model has the probability distribution. So you have the absolute correct prior, and this just feels very satisfying. So where do we go from here? So the first thing that I want to bring back to, and just going back to the first part of the talk, is that I think that we really need to rethink parameterized quantum circuit-based quantum machine learning. Why do we expect that quantum computers will be good at processing any type of information? I honestly don't think that this is going to be the case, but again, I'm willing to be proved wrong. And I think that we need to think outside of the box. As an example, this Gaussian process regression, where we're not claiming quantum advantage. We're still exploring what this can do. And I'm just cautiously optimistic. This is something that, I'm interested in pursuing and learning more. And if it doesn't turn out, well, we've unlocked this new idea of maybe going back to quantum data to classical algorithms. And the question is, maybe even if there is this sort of non-zero chance that we can find some use case for quantum machine learning, the question is, and maybe this is what I want to try to convey to students, is how much do we want to search that haystack for that needle? Maybe there are some use cases, but are we really going to be spending how much time? When will we hit diminishing return in this quest? And if you want to pursue this, is completely fine. I think this is a noble pursuit. But what I would mention is, and this is taken from Maria Schultz's paper, Better Than Classical: The Subtle Art of Benchmarking Quantum Machine Learning Models, which is a really great paper, is you need to be aware of positive bias. It's this idea that if you go out there to try to prove that quantum machine learning will give a quantum advantage, you will certainly be able to do this. You will find a comparison with a classical model that works. You will find a model that happened to work well, and So the question is, do we want to try to understand if quantum machine learning can give a quantum advantage, or do we want to prove that quantum machine learning will give a quantum advantage? And even if those two questions sound very different, they're very similar, they're fundamentally different. So with that, I just want to thank you all for your attention. If you have further questions beyond this, this is my email. If some of you are going to be at QTML next week, I'm traveling tomorrow over there, so we can just chat over there. And also, every year, LANL holds a summer school, and we will open applications for this summer school next week. So with that, I want to thank you and the organizers for the attention and this opportunity to share our thoughts.
Thank you very much, Marco. It was really awesome. So the microphone is ready to be open for any one of your questions. So just click on the raise hand, and we will unmute you. So don't be shy and go ahead. Okay. See, there's one question, two questions.
Okay, Alberto, you are on mute now.
I think the mic is not allowed.
I think that from my side, it's allowed.
Okay.
But I'm second.
Okay. Javier.
Yeah, please, Adrian, go ahead.
Yeah. Hi, Marco. Thanks for the talk. I enjoyed it a lot. I wanted to ask you something a bit broad about what kind of perspective do you have for this all variational quantum computing and quantum machine learning in particular, which is, I think that we have been gathering this kind of negative results of trainability and Barren plateaus and simulability, because we were kind of looking to the wrong directions. So do you think we have been over optimistic at the beginning, saying we have one quantum model to rule them all, and we have to tune down a little bit our expectations?
Yeah, I think so. I think that, one of the reasons why I have been in this quest to talk to people about some of the difficulties of variational algorithms is because when we wrote our review article in 2001, we were overly optimistic. If you read that, it seems almost like variational and quantum machine learning can solve pretty much all the problems because we hadn't encountered these issues. So I think that there was a huge way of optimism. A lot of that I partially feel responsible for fueling through our overly optimistic review. And I feel like now I'm on like redeeming quest to try to tell people, well, let's not get that excited. Maybe there are some difficulties. So I think that we need to temper of expectations because again, like it's been 5 years of research. And if you have some method, variational method that you're confident that you would bet your money on, then let's chat about it. But I certainly don't have one. So I think that, yes, maybe we need to fine tune a little bit more, but the fact that solving the issues takes us to classical simulability, it's just math, like it's the math telling you something, and we should try to interpret those results. It's kind of like where I'm currently standing at.
I definitely agree. If I may speak again, there is this question in the chat. Alberto seems not to be capable of. So whoever the host, maybe speak up.
So I can see Alberto's question. I can just read it out loud. You mentioned that QML would likely be inefficient when dealing with large amounts of data because of the complexity of encoding that data to fit it to the quantum computer. But what if the data is already quantum? In that case, you may skip the encoding phase, right? I completely agree. If your data is quantum, then you can completely skip it. And I was, for a while, very interested in trying to use quantum machine learning for quantum data. And in particular, I did a PhD in condensed matter, so in phase detection. So can we use quantum machine learning models to try to learn phases? And there's a bunch of papers out there, and you can always train a quantum machine learning model to classify phases. And you have these very nice plots where you have like a paramagnetic phase, an anti-paramagnetic phase, and a topologically protected phase, and your model does really good on this. But the question is that, for me, those problems are trivial. Because if you think about it, I can do that classification by measuring a single qubit or two neighboring qubits. If it's a ferromagnetic state, the expectation value of ZZ is going to be positive. If it's an anti-ferromagnetic space, it's going to be negative because it's kind of like spins like this. And if it's topologically protected, it's 0. So is a quantum learning model doing actually something useful? I don't know. I don't think so. It's kind of like very trivial data sets because identifying topological orders is an extremely hard question. And this is not what the quantum learning model is doing. It's just telling you, oh, this state is trivial or this state is not trivial, which, I can just measure a single qubit and do this. And I really encourage you, if you're interested in quantum data, to go and look at our quantum convolutional neural network paper and also Pablo's talk here in Quantum Spain, because we argue that all the data sets that we're using for quantum data, they're kind of trivial. You don't need a quantum learning model. You can just do like fidelity kernel or just like fidelity susceptibility, as people call it in condensed matter community, no training anything, and you can do phase classifications. So it feels like we're reinventing the wheel in a way which is completely necessary. And all of those successes is because we're training models on trivial problems that can be solved by measuring a single qubit. So yeah, I don't know. I'm excited about quantum data, but I haven't found any place where I've seen super convincing results again.
And I think there is another question on the chat.
Oh, yes. I see a question by Herman. The way you present the Barren Plateau reminds me of the orthogonality catastrophe in condensed matter physics. There will be a relationship between both. So I want to be honest, I have no idea what the orthogonality catastrophe is, and I don't want to venture a guess without knowing what I'm getting into. So if you see some connection, write me an email, or if you can unmute yourself and explain this to me, I would be very happy to chat. But if you see a connection somewhere, trying to figure out how people deal with this somewhere else could be interesting.
Yeah. Okay, so any more questions? So just let me throw one. So just try to get something useful out of here of everything. So I always try to gather the learning from the short algorithm. There's somebody found a useful problem for a known solution. So you went backwards, yeah. So I wonder if this is the lesson that we should take over here. So supposing that this quantum Gaussian process regression really fulfills all expectations and really proves to be, is the family of problems well characterized that one can treat with this, or is this not a constraint on the problems that you want to?
It is definitely very much constrained. And in a nutshell, for people that are familiar with classical shadows, the type of problems with Gaussian process regressions are exactly the same where classical shadows work. And if we can discuss the deep representation theoretical reasons why, but yeah, we're kind of like fairly certain that we understand what are the cases that it's going to work, and it's not going to be something that will always work. It's kind of like a specialized tool for certain like very structured problems. If I may give a recommendation, because you mentioned Short's algorithm and I just mentioned representation theory, I think that for people who want to try to understand why quantum algorithms work, it's all like representation theory, and this is, I think, what Maria talked about, which is like the underlying structure of quantum algorithms is that of group theory and representation theory, and it's super interesting to see, how the hidden subgroup problem emerges. So for us, the most powerful tool that we've used to try to find cases where this is going to work is representation theory. So if I can give an advice to people is learn group and representation theory, because this is the only tool that I use nowadays.
So this was hidden in your presentation. This Gaussian process regression was this reasoning was hidden. This hidden subgroup problem. So
not in this case. This is just for standard quantum algorithms like quantum Fourier transform algorithm. But in our case, we can understand what are the cases where this is going to work by using representation theoretical tools. This is kind of like the proof method that we use to show that this will be a Gaussian process, because to prove that a random variable has a given distribution, you need to compute all of its infinitely many moments. So this is kind of like what we're doing.
Right. Excellent. So I think we are almost round the clock.
Just one final question on the chat.
Good.
Okay, so Tanya asks, on the topic of variational algorithms as a whole, many positive results are coming out in regards of QAOA. Smart initialization strategies seem to yield good results while avoiding the Barren Plateau problem. Do you believe that all variational algorithms are inherently useless? No, I do not believe that. And I have no way of proving this. And again, I try to rely on solid science, and I will never dare to make such a comment, because here's the thing. If you manage to find an optimization problem where QAOA can give you a 5% increase over the best classical algorithms out there, that would be huge for industry. That would absolutely be huge. Now, my intuition is that that's going to be very fringe. It's going to be a very special kind of problem. And I don't think it's representative of what those papers are doing out there, because if you take Erdos-Reni graphs and you're training QAOA on them, parameter transfers works really well because all graphs locally look the same. So if I have a 100 node graph or 1,000 graph node, locally they will statistically look the same. But so all those margin initialization, parameter transfer strategies work like super well there. But if I give you a realistic problem of like an actual distribution route, I don't know if those tools will be useful. So again, this is one of those things where I feel like there's a disconnect between what we're doing in practice in the papers to benchmark and the problems that we're going to be trying to solve. And I think that that's fine to sort of like ourselves learn how the models work, learn good practices. But I don't think we can only rely on that. So again, I'm pessimistic, but I wouldn't tell people there is no way that variational algorithms will work. I definitely don't feel comfortable saying that. And again, if someone manages to find a good use for variational algorithms, I'm going to be extremely excited about that. Like I'm going to be the first one to go out there and be like, this is great, we've made it.
Yeah. Yeah, I have a last question. In many times where the variational algorithms work is because you have a physically inspired initial condition. In many of those cases, you don't see Barren plateaus. So do you think these are all classically simulable?
So there's this really nice paper by Garnet Chang and the Google group on quantum chemistry, where they're analyzing VQE for quantum chemistry problem. And as you said, if you have a really good initialization strategy and a really good initial state, maybe you're getting this as Hartree-Fock approximation or some more advanced self-consistent Milfin theory, and then you're putting an ansatz that is appropriate and it's physically inspired, like the unitary couple cluster and ansatz. Well, what they kind of hint at is that the cases where you can get a really good initialization strategy that is going to get you sufficiently close to your solution that training is almost guaranteed are precisely the ones where classical methods work really, really well. Whether this is a fundamental property of the world, I do not know, but it's just, again, hinting at this fact, like, like after a while, there's so many facts like in front of you that you have to address them. And this for me was like very surprising, that the problems where they found that VQE works well are the problems where classical methods work really well. On the other hand, they do say that maybe there's a possibility for very small constant order improvement, which for industry could be huge, So if that's what we're aiming for, then, we should definitely pursue this. But pursuing this in a realistic sense is what I'm saying, like add shot noise to the experiments. If you're aiming for noisy quantum computers, add noise. Like I think after 5 years of variational algorithms, we should not have plots that don't have finite samples. That is kind of not the benchmark that we should aim for. I don't remember the name of that paper, Marcio, today, but I know that Brian Babush is in there. Garnet Chang is in there. We also cited in our paper, does provable absence of Barren plateau imply classical simulability? It's in a footnote because we make a specific comment about that. So
I'll look at that.
I can point Marcio specific to the place where you can find that reference.
Thank you. Awesome. Okay, I think there's one. There's still one. Is there one question, Javier? Or it disappeared? It went to the chat. Disappeared. Okay, so I think we're done. I want to thank warmly Marco for sharing with us this hour and his insightful comments and views. And stay tuned. We'll be back in 2 weeks and maybe break for Christmas. So thank you, Marco, and goodbye, everybody. Have a nice time. Goodbye.